Our next section is going to cover Venn diagrams and different types of set operations. So if you think of drawing a Venn diagram, it's still going to have the same kind of concept here as it does when you did it in English. So we know Venn diagrams were super useful when you were having to do like character dissection. So you had two different characters and you'd find traits or something they had in common, or maybe they're from the same location. But then there were things that were unique to them. So the characteristics they shared went in the center of the Venn diagram. Things that were unique to them went outside that centerpiece, but inside their own circle. And then things on the outside of the circle didn't pertain to either of the characters. It's still kind of the same thing here. So we're going to use a rectangle to represent our universal set. So this is going to be all of the elements I'm considering for a problem, and they need to find a place in my Venn diagram. So you'll see a box always, and then this is where we use that U to say, here's everything I'm considering for this particular problem. Now we're going to have two subsets, A and B, which are just going to be selections from U. Okay? A Venn diagram is going to be really helpful to determine how they're related. So when you create a Venn diagram, you're always going to end up drawing it the same way to start, but then depending upon where the elements are placed, you might be able to make a better looking Venn diagram. So what I want to do is I want to show you some possible options as to what could happen based on the Venn diagram you create. So in one possibility, maybe I have my set A here, and then set B ends up being able to be a completely distinct circle, okay? So in this case, there's no overlap. I wouldn't draw these circles on top of each other because there's nothing in common to the two. So in this case, we would say these sets are disjoint. Okay. So each circle is representing the set itself, and you would put all of the elements just in a list or however inside of here. And in this case, because there's no overlap, they are disjoint. So A and B are disjoint. So they have no elements in common. So this is the best way to represent that. Again, when you're starting a problem, you're always going to draw your Venn diagrams like this. But then it would be, once you list everything, you would see the center part here would be completely empty. So the better way to draw the Venn diagram would to show two separate circles. Another possibility is maybe my set A, I could draw here, and set B is completely around it. Okay, so maybe I have some numbers in here, like say 1, 2, 3, but then the numbers 4 and 5 go on the outside. So this would mean the numbers 1, 2, and 3 are also in set B, but I've got these extra pieces 4 and 5 that belong to B as well. So if this is the case, then what happens is A fits completely inside of B. So these are actually a good representation for subsets. Okay. So when A is a subset of B, every element in A is also in B. So what we do is we can fit A's circle completely inside B. Okay. And again, there's likely stuff on the outside because otherwise these two would be equal. And that's actually our next scenario. So if it happens to be the sets contain the same elements, this one's a little bit harder to draw, but here is set A. And it happens to be that set B is the same. So what I'm going to do is use a highlighter to draw right over top of it. And then I'll also just make this dotted so it looks a little bit different at least. Well, let's do dash, that looks a little better. So these would share exactly the same elements. This would be our representation to show they are equal. So when A equals B, the sets are the same circle. Okay. So again, these are very certain circumstances that you're not going to know until you draw your Venn diagram. Maybe you can recognize it from the start, but that's typically hard to do. Okay. So realistically, what you're going to do is I'm going to start by drawing my set A. And then I'm going to overlap that with set B. Okay. So this means I have to place all of these elements somewhere inside B's circle. And likewise, I have to place all of A's elements somewhere in the circle. But this middle area here would be part of both circles. So this would be where they overlap. So if this has some stuff filled in, these are just overlapping sets. This is the most common picture, again, you see for a Venn diagram, and it's what you start with. Then you see, can I go into one of these other unique situations because of how the Venn diagram looks? Like if this is empty, that means there's nothing unique to A, so I would be able to actually draw my picture like this. If I go in and fill in my Venn diagram and this is empty, there's nothing in common, so I would go back up here to draw a disjoint. And if it happened to be that this was the only thing filled out because they're exactly the same, so there's nothing unique to either set, then you would go back up here and say, okay, they're equal. So here A and B have some elements in common. But they both contain at least one element, the other does not. So regardless of the problem, what I'd always recommend doing is drawing a Venn diagram for that situation, because that's going to be very helpful when we're dealing with set operations. Otherwise, it can be very easy to kind of mess things up. Now, granted, it is going to be much easier on a tablet when you can use a highlighter to help shade things in too. But you might have to just draw a bunch of pictures of the Venn diagram to see the regions that you're talking about. So before we get into all of those operations, I kind of want to just get familiar with creating a Venn diagram. So we're going to construct a Venn diagram for the sets, and we're going to place these elements in the proper region. So again, always to start out, I'm going to draw my Venn diagram to begin with. The box represents you, so that means all of these numbers 1 through 8 better find a home in the picture. The numbers 1, 6, and 8 belong to A, so they better get placed somewhere inside of A's circle. And likewise, these numbers better get placed somewhere inside B's circle. Personally, when I go about these, I always like to start right here in the middle, okay? Because otherwise, if I start jumping in, okay, I got to place 1, 6, and 8. Let me see, where does number 1 go? Okay. Well, it's here, it's in A, it's not in B, so that means it has to go out here. Then I got to go down the list. That's complicated to me. Instead, I like to look at the overlap. So if I consider 1 is not in this set, however, if I look at the number 6, that belongs to both. And likewise, the number 8 is inside both sets. So immediately that tells me the numbers 6 and 8 have to go into that middle region. So this is what's common to A and B. Okay. The other thing I like to do is, again, the numbers 1 through 8 have to find a home. So I'm going to go ahead and I'm going to mark off 6 and 8. They found a spot in my diagram, so I don't have to worry about them anymore. Now that I've got that done, I can go back into set A. I've got number 1 here that doesn't have a home yet, but that's unique to A. So it's going to have to go here in the left. It's part of A, but it's not common to B. So the number 1 is going to go off to the side. So that is unique to A. And then again, I'm going to go ahead and mark that out of view. It's got a spot in my diagram. Then moving on to the numbers 2, 4, and 7. These are the ones that are unique to B. So they go off to the side here. Okay. And again, I'm going to go ahead and mark those out of my set U. And then finally, I've got these 2 numbers, 3 and 5, that have not found a spot in my diagram. They're not inside set A, and they're not inside set B. They're still, however, important, so they just have to go on the outside because they're part of U. So these are the elements not used yet. They go on the outside. And now I can go ahead and mark those off. These found a home in my diagram. So this is a visual representation for this set. And again, the way I can read this now, anything inside this circle is set A. So set A contains the numbers 1, 6, and 8. Anything inside this circle is what's in set B. So that's 2, 4, 6, 7, 8. Try to put it in order when it's numbers. 6 and 8 is the overlap between these 2 sets. And then 3 and 5 do not belong to either one, but again, they're part of U. So this outer box tells me all of the numbers 1, 2, 3, 4, 5, 6, 7, mark those backwards, and 8. Those are all of the numbers inside of set U. Okay? So this is our Venn diagram for these particular sets. And again, anytime, because we're about to do set operations, you need to go through that. I'd recommend drawing a Venn diagram even if it doesn't say to. It is very helpful for a picture. Because now I can utilize this because I can start shading in things that I need. I don't need to fill in the numbers every single time I draw it, but at least this way I can get an idea for the sections I'm talking about. Because really what ends up happening is if you look at this, it's split into pretty distinct sections. There's 1 region, 2 regions, 3 regions, 4 sections of my Venn diagram that I'm talking about. Okay? So what we're going to do now is we're going to go through all our different set operations, the symbols for them, and what it actually means. And then we're going to try an example with a ton of operations and tie everything in together. So first and foremost, we've got the complement of a set A. The way we denote this is it's just dealing with set A. It's kind of like an apostrophe, but not quite. It's called a prime notation. This you can think of as the phrase not in. So if you think of complementary colors, they're opposites on the color wheel, like blue and orange, red and green are complementary colors, purple and yellow, complementary colors. So they're opposites. That's exactly the same kind of thing here. It's the opposite of what's in A. So the formal meaning is these are the set of elements in U that are not in A. So I'm going to go back to the previous Venn diagram to just kind of shade stuff in so you can see what I mean. But here is set A. So its complement would be everything except this circle. So the complement of A would be anything on the outside here. So this would be the numbers 2, 4, 7, 5, and 3. That's the complement of A. Because together these two things form the entire region U. Likewise, if I find the complement of B, what I do is I ignore B's circle, which is this one right here. So the complement is everything except that. So the complement of B would be 1, 3, and 5. Okay. The intersection of two sets here, A and B, is what I hope you think of with intersection. So the intersection of a road or two roads is where they overlap. It's the same thing here. So the way we denote this is we have A and B. The intersection is symbolized by an upside down U. And again, this means end. So it's in A and in B. So this is the set of elements common to A and B. So utilizing this picture, the intersection of A and B is just that middle. So it would be the elements 6 and 8. Okay. Last but not least, we've got the union. And this is again where I told you we're going to have a symbol that looks like a U. It is the flip of the intersection. No foot on it. It is just a U. The phrase you can think of here is or. So the thing I associate with unions is the union of marriage. That's two people joining their lives together. Everything gets combined into one. If one's got debt, the other's got debt now. If one's got money, the other's got money now. It joins them together. Same thing, you think of the Union of the United States. That's technically what we are. It is all of the states joined to make one big country. So it's joining all of these pieces to one. So the way we describe this is the set containing the elements that are members of A, B, or both. So if I go to this example here and I look at the union, I'm really just going to meld these to one giant circle. So the union would make not a circle, but one welded together piece. So the union is everything putting these two together. Okay. So when you go through, if we have a bunch of operations, because I can combine all of these, I could say let's take A complement intersect B. I could say take A union B and then take the complement. You have a lot of possibilities for set operations. So the thing you want to think of is your order of operations. We have that phrase, please excuse my dear Aunt Sally, which is PEMDAS. You should always start by doing things in parentheses, so find the sets inside of parentheses. E stands for, well, then I should do exponents, and that complement is in the exponent spot, so you should do that first. Then all of these, we really don't have multiplication, division, addition, or subtraction in set operations, so that's what we do for union and intersection. It's kind of just the similar type idea. So you should start by looking in parentheses. Within parentheses, then I want to move to that complements. Then I move into intersections and unions. So let's try a bunch of these. and we'll also get some more practice with creating a Venn diagram. So given this set U, one has the numbers 1 through 8. Here's sets A and B. We're going to complete the following. So first we're going to construct a Venn diagram, and then we're going to find a bunch of different sets and then refresh with some of our other terminology. So first and foremost, I want to make this Venn diagram. And again, I'm going to go about this in the same way. I'm going to start with the overlap in the middle. So if I look at these two sets, they have the number 2 in common and they have the number 5 in common. So I'm going to mark those out of view simultaneously, but 2 and 5 go in the middle. Then I've got these numbers that are unique to A, which are the numbers 1, 4, and 7. So I'm marking them out of view because they are finding a home in our picture. 1, 4, 7. And then finally, 3 and 6 are unique to B. So I'm going to go ahead and mark them out of U. They get placed off to the right. Last but not least, I have a single number that hasn't been used, which is 8. So that belongs on the outside. So I'm going to utilize this Venn diagram to answer these different questions. Now what I'm going to do is I'm going to basically draw a mini one right here. I'm not, however, let me make it so it's actually a rectangle. I'm not, however, going to fill in everything, so I don't fill in the numbers. I'll revert back to my original diagram for that. But I really like to use these. I wish it would. All right, 3rd time's the charm. Let's see. I think this might be the 4th, but that's okay. There we go. So I'm going to use this just to be able to shade things in. So we've got our sets A, and then we've got our set B as well. And I want to use this really for every single problem. So I'm going to go ahead and cheat as well, and I'm going to duplicate it and bring this down a bunch to make life easy. Okay. So starting out with the union, remember this means or. So it's anything that's in A or B. So if I think about that region, these are the things in A, these are the things in B. So anything in that shaded region belongs in the union. So going back up here, that would be anything within these two circles. So pretty much everything except the number 8. That's the only thing not in that region. So A union B is the numbers 1 through 7. Everything except 8. Okay. Next up, we want to find the intersection. And so again, the intersection means end. So these are things that are in A and in B. So end is very selective. It's got to be both of them. Or is more relaxed. As long as it's in one, it's in the or the union. So in this case, my intersection is just that middle region. So going back up here, that intersection is the numbers 2 and 5. So this particular set, A intersect B, just contains the numbers 2 and 5. Okay. Moving on to this third one, I've got 2 operations here. I've got a union and I've got a complement. So again, following those order of operations, you go in parentheses first. So the first thing I need to do is find A union B, and then I take the complement. So the way you could think about this is these are things that are not in A union B. Okay. So I want things that are not in the union. You can utilize the set back up here. Here's the union. The only thing not in there is the number 8. But again, if I want to use pictures to help me out, my union is this. So when I go to find the complement of the union, it's everything I didn't shade. So it is solely the outside. So the way I personally like to do these is I actually like to black out that set. So A union B is this. So the complement is the outside. So going back up here, again, this section on the outside just contains the number 8. But again, these kind of go hand in hand. So here's the union. The complement is everything except the numbers 1 through 7. So A union B complement just contains the number 7. Okay. Moving on to this next one, I've got to find the cardinality. So this is the number of elements in A complement intersect B. Well, that means I need to find A complement intersect B first. So again, going through my order of operations, I don't have parentheses, so I've got to start with A complement. Okay. And so here I'll actually go ahead and rewrite those numbers because I think that's going to be helpful than scrolling back up. So 1, 4, 7, 2, 5, 3, 6, and 8. Okay. And I'll rewrite those here. Because I don't want to scroll up and make this very confusing. Okay. So if I start with A complement, again, I'm going to black out A circle. So the complement is everything except that. So it's 3, 6, and 8. Okay. And I want to intersect this with B, so I'm going to show you how to do this just by writing the sets too. Looking at B's circle, that's 2, 3, 5, and 6. So if I want the intersection of these two, I'm looking for the overlap. So I'm finding what they have in common. They both contain the number 3. They both contain the number 6. So 3 and 6 is the intersection. So the number of elements in A complement intersect B is 2. Contains 2 things. Okay. Again, if you want to use pictures, absolutely. So starting out, again, I've got to find A complement. So we black out A's circle. And the complement is everything on the outside of that. So 3, 6, and 8. So I'm going to leave that up because that's our first region. Then looking at set B, that's right here. Okay. When I want the intersection, I'm looking for where does the shading overlap. So in that case, the overlapping shading is just the section that is unique to B. So it is just the numbers 3 and 6. Okay. Let's try one more of these. And this one's going to be the number of elements in A union B. This one's a little nicer because, again, we've already found the union. It is the numbers 1 through 7. So A union B is 1, 2, 3, 4, 5, 6, 7. So the number of elements here in can go ahead and count those up, but it's the numbers 1 through 7, so it is 7. Okay. The number one mistake that happens here with the union, and really I'm doing this because if you're going to go on to learn about probability and take some of our other courses that involve that, this is an important concept. When you have or, there is that overlap. So the most common mistake that happens is if you find the number of elements in A and the number of elements in B and add them together, you think that's the number of elements in the union. But what happens here is if you look at the number of elements in set A, that's 1, 2, 3, 4, 5 elements inside of it. The number of elements in set B is 1, 2, 3, 4. So what happens is if you add these together, it gives you 9 because you end up double counting the middle section. Okay? So when you're finding the number of elements in A union B, you can't just add them together. In this case, in the last example, you double count the numbers 2 and 5 because they belong to both sets. So really what happens for any finite sets B, if I want to find the number of elements in A union B, you can just find each separately. But what I need to do is I need to take into account that I'm double counting the middle, which is the intersection. So I have to subtract the number of elements in A intersect B. Okay? So this is really helpful, again, in probability. If you think about, if you've learned that at any point in your life, best example is kind of with cards. If you're finding the probability of drawing a jack or a spade from a deck of cards, you can consider the probability of getting a jack and the probability of getting a spade, and you could add those together, but the problem is the jack of spades, you're double counting for each of them. So you have to subtract the probability of getting a jack and a spade. So it's a nice formula that just has a nice extension, okay? What we're gonna do is we're gonna utilize this for a word problem, and I'm also gonna show you a way that you could just do this with Venn diagrams as well. So Winter Resort took a poll of its 400 visitors to see which winter activities people enjoyed. The results were as follows. So 198 people liked to ski, 264 liked to snowboard, 132 people like to ski and snowboard. We want to figure out how many people like to ski or snowboard, okay? So I'm going to let A be the set of people that like to ski, and I'm going to let B be the set of people that like to snowboard. Okay. So really what this is then is the number of elements in set A is 198. The number of elements in set B is 264. This end, remember, is the intersection. So this is the number of people that are in A and in B. What I want to do is we want to figure out what is the union, how many people are in that, okay? So using our formula, the number of people that like to ski or snowboard is the number of people that like to ski plus the number of people that like to snowboard minus the fact that I'm double counting some of them. So this is 198 plus 264 minus 132. Okay. So if you go through that, you should end up with 330 on your calculator. But give it a shot to double check. Okay. So that's one way you can go about this problem. But like I said, you don't need to use the formula for this. As kind of a prelude to our later sections, I'm going to show you this also with a Venn diagram. So I'm going to just do that kind of small over here, and you'll see we end up with the same thing. If I could make this thing make a rectangle today, that would be great. There we go. So we've got our snowboard circle and our ski circle. And if I go ahead and consider these numbers, get rid of this to make it a little cleaner. The number of people that like to ski and snowboard is 132. So 132 is that overlap. Okay, make that a little more clear. Now for this next part, they tell us 264 like to snowboard. So what I need to do, this entire circle should be 264. I've placed 132 people in the center. So the number that just like to snowboard is I take the total amount and I subtract how many people I've already placed. And if I do that, not the best numbers, because I end up with 132. So there are 132 people that like to snowboard but not ski. Okay. Then I do the same thing with this 198. 198 is the entire ski circle, and I've placed 132 in the middle. So from that total amount, I need to account for that. So the number of people that just like to ski is 66. Okay. And now if I want to see the number of people that like to ski or snowboard, I just go ahead and add these three together, and it should give me the exact same thing. But just for completeness, there's technically a part of this I haven't filled in, which is the outside here. And that's where you're going to use the fact that we polled 400 visitors, because some of them don't like to ski. So what I'm going to do is I'm going to figure out the outside. We need 400 people in total. We've placed 66, 132, and 132, which leaves us with 70 people that didn't like either of these sports. Okay. So that's my most complete diagram to be able to answer further questions. But now the number of people that like to ski or snowboard is going to be the 66 that just like to ski, the 132 that like both, and then the 132 that just like to snowboard. And in the end, you still up with the same answer. 330 people like to ski or snowboard. So results in the same thing. So either way, perfectly fine to do these problems. Again, this is really helpful for later sections when you have to answer more questions.